Welcome to this video. We are going to look at chemistry assignment 2. So this assignment has questions on atomic structure. We're going to try to solve all of them, okay? And then I think the last two questions are on chemical equilibrium. These ones here, you can see question 7, question 8. That's chemical equilibrium, okay? So we start with question 1, which is on atomic structure. Okay, so let's start with question 1. Okay, so question 1 is asking about us to find the change in energy. So you can see here they're saying how much energy in joules is liberated when an electron changes from N5 to N2. So here, let me just explain the concept and then I'll come back, okay, and solve this question. So the electrons in the atom, they undergo what we call as transitions. Okay, so transitions are just movement within the atom. Okay, so they will change the energy shell where they are. So remember, at secondary level, we used to draw the atom like this. We said we had the nucleus, okay, there. And then around this nucleus, we had these energy levels like this, if you can remember. Okay, so these energy levels contain what? We said these energy levels, they are containing electrons. So you can have electron there, an electron there, an electron there. Okay, if you remember this. So these electrons can move, okay, from one energy level to the other. So these energy levels are represented by what we call as N, which is the principal quantum number. So this is the first shell. So it will be N1. This one is N2. This one is N3. Okay, so these electrons, depending on where they are, they have a discrete amount of energy, okay, in each of these shells. So it happens that these electrons can move, okay? If an electron is there, for example, okay, it has higher energy than the one which is there. So this electron can lose energy. So once it loses energy, it collapses to a lower energy level. So this electron here can collapse and it can come there, okay? So it has what? Lost energy there. If it's coming from a high energy level to a lower one, it has lost energy. And then also, these electrons here can gain energy and go to a higher one like this. Okay, so it is in the lower and then it has gone to a higher one. So it has gained energy here. Okay, so the amount of energy that an electron has, okay, in a specific energy level is given by the formula energy, okay, is equals to minus 2.178 multiplied by 10 to the power minus 18. And then in the brackets, I'm going to put z squared over n squared. So what is the z squared? Okay, so z squared is just the atomic number. So in most of these questions, okay, if they don't state the atom that you are dealing with, you are going to assume that the atom is hydrogen, and hydrogen has the atomic number 1. So that's why you find that in most cases, okay, when in most books, okay, when you're given this formula, it's just going to be in this form times 10 to the power minus 18, and then 1 over n squared. Okay, this one comes in because we are dealing with hydrogen. So hydrogen has the atomic number of what? Of 1. So this formula here, okay, it's the one that tells us the amount of energy that a certain electron has in a specific energy level. Okay, so if it is in energy level number 2, for example, this should be 3. If it is energy number 2 here, you are going to put 2 squared, and then you just punch onto the calculator. That would be the amount of energy, okay, that hydrogen electron has, okay, in that shell, okay. And then I said that these electrons can move, right? So you find that some electron was here maybe, and then it has lost energy. It's now in the first energy level, okay. So to find the lost in the energy lost or the energy liberated, then this electron, okay, was in N3 and now it has dropped to N1, okay. We're just going to use the following formula. We're going to say the change in energy will be equals to, okay, the energy that it has here, which is minus 2.178 times 10 to the power minus 18. We're assuming that this atom is hydrogen, and then 1 over. So this here is N3. So it will be 3 squared, okay, like this. So this is the energy that it has here in energy level number 3. And then it has gone, okay, it's now at energy level number what? Number 1. Okay, so you also find the energy that it has in that one. So it will be minus 2.178 multiplied by 10 to the power minus 18 over 1 over, okay, the value of n is 1, so that will just be 1 squared. So we can see here that in N3, it has this energy, right? Okay, in N1, it has this energy. So how do we find the energy that was lost for it to drop into the first energy level? We subtract, okay, the energy of the final, where it is, minus the energy from where it's coming from. Okay, so we can say our N3 was just our N initial. Okay, so we're going to say N initial is equals to 3. This I means initial. Then our N1 is our final energy level. So that will be our F final is equals to what? To 1. Okay, so we can just combine these formulas instead of finding the individual energies there. We can combine this formula into 1. Okay, so remember we said the energy, okay, for the lost in energy will be this one minus this one. So if I write this one first, it will be minus 2.178 times 10 to the power minus 18, 1 over 1 squared minus, and then I have this one minus 2.178 times 10 to the power minus 18, and then 1 over 3 squared like this. Okay, so we see that from here, we can see this guy here is common. So we factorize him like this. Okay, and then what are we going to remain with? I'm going to remain with 1 over 1 squared. Okay, and then this minus 1 over 3 squared. Okay, so this is the formula that we are going to be using to find the change in energy. We're going to put here our N final, we square it, minus there we're going to put our N initial, and then we square it. Okay, so now that I've explained, let's just use the formula there. Okay, so I'm assuming that this atom here is hydrogen. So it means the Z is just 1. So meaning Z squared is still 1. Okay, so I'm going to say the energy liberated, or the change in energy, okay, from N5 to N2 will be given by minus 2.178 times 10 to the power minus 18, and then 1 over. So here we are coming from 5 to 2. So it means my N final is 2. My N initial is 5. So it will be 1 over the N final squared. So 2 squared minus 1 over the N initial, which is 5 squared, like this. Okay. So what do we get here? We get minus 2.178 times 10 to the power minus 18. And then in the brackets, we have 1 over 4 minus 1 over 25. Okay, so this is what we have. So we can just say this is equals to minus 2.178 times 10 to the power minus 18. And then this one, we can put them together. So that is 1 over 4 minus 1 over 25. So common denominator here is 10. And then 4 into this 100 to give you 25. 25 multiplied by, is it 25? 4 into 10. I mean 4 into 100. Okay, 4 into 100 is 25. Okay, so that would be 25. Then minus, okay, here it is 25 into 100. That is 4, right? Okay, so 4 multiplied by 1, that is 4. So if I subtract, I get 21 over 100. Okay, so what is left is just to punch this whole value onto the calculator, and then you get the final answer. Okay, so counter check with your own calculators. Okay, so if I punch this on my calculator, I'm getting a minus 4.5738 times 10 to the power minus 19, and this energy is in joules. Okay, this energy is in joules. Okay, so that's what we get there as our energy liberated. So this one here, the negative sign, simply means it's the energy lost. Okay, if it's the energy gained, you're going to find there should be a positive. Okay, so because it's energy liberated or energy lost, okay, no wonder we are seeing that negative there. Okay, so once you find this, so you can just write down there, you're going to say, therefore, the energy liberated, and then you omit the negative sign. So you're going to say energy liberated, okay, is 4.5738 times 10 to the power minus 19 joules. So this is the energy that was liberated. Okay, so we found the energy. We can move on now to B. So B, they're saying, what is the wavelength in nanometers of this radiation? So there we're going to make use of this equation. We're going to say energy is equals to Planck's constant multiplied by the speed of light over the wavelength. So we can make the wavelength the subject of a formula here by cross multiplying. okay, and then dividing both sides by E, we're going to get wavelength is equals to hc over E. Okay, so now h is the Planck's constant. So it has a value of 6.626 multiplied by 10, multiplied by 10 to the power minus 34. So this is the Planck's constant, the h. And then c is the speed of light. We're going to be using 3.0 times 10 to the power 8 meters per second. This one is just joules meter like this. Okay, and then from there we can calculate this guy here, the wavelength. So the wavelength will just be equals to the h 6.626 times 10 to the power minus 34 multiplied by the speed of light 3.0 times 10 to the power 18 divided by the energy which we found, which was 4.5738 times 10 to the power minus 19. Okay, so what is left here is just for you guys to punch this onto the calculator. Okay, so when you're punching this onto the calculator, make sure you put brackets. So you write this number in brackets like this. You say multiplied by, you put this number in brackets. Okay, and then you divide by this number in brackets as well. So what I'm getting there is 4.34 multiplied by 10 to the power minus 7, and this will be meters. Okay, so that is my wavelength in meters. Okay, so why are we getting meters? Because remember the Planck's constant is joules per second, this guy. Then I'm multiplying with the units for speed, which is meter per second, and then divided by the joules. So the joules and the joules goes. The S and the S, they go. Just remain with the meter. Okay, so this is the meter that you're seeing there. So that is our wavelength, but in meters. Okay, so we have to change it to nanometers. So how do we do that? Okay, we just use simple conversions. Okay, so we know that nano. Okay, we know that nano means 10 to the power minus 9 like this. Okay, so I just want to express this so that it has a power minus 9. Okay, so for it to have a power minus 9, what do I do to it? So I have to move this decimal place here. I have to move it 2 times to the right like this. Remember, when you go to the left, we subtract from the power. Okay, when you go to the left, we add. So this number, the way it is, I can write it as lambda is equals to, okay, 434 multiplied by 10 to the power minus 2 multiplied by 10 to the power minus 7 meters. So this guy here, okay, simply means I've moved this point 1, 2. Okay, and then these ones are the same. So I can combine them to just get 434 times 10 to the power minus 9 meters. So this is what I have. I have my lambda is equals to 434 times 10 to the power minus 9 meters. Okay, but nano from the metric system is just 10 to the power minus 9, this guy. So I'll just replace this guy by nano. So it will be 434 nanometers. So this is the wavelength in nanometers. Okay, and we are done. So if you don't want to use this approach, you can still use the ratio approach. You say 1 nanometer, okay, is equals to 10 to the power minus 9 meters. Okay, and then you put the meters that you had there now, which is 4.34 times 10 to the power minus 7 meters, and then you put x. Then you cross multiply, you find the value of x, you're still going to find this guy. Okay, so this is just a smarter way to avoid the cross multiplication. So use whichever is better for you. Okay, and then C, we have a very interesting question on D. They're saying what type of radiation? Okay, so remember our lambda is 434 nanometers. So they're saying what type of radiation is this, and then which series does this light belong to? Okay, so here a very clever way is first to state the series, and then you know the type of radiation. Okay, state the series, and then you know the type of radiation. So we have 5 series. So this series, okay, this series are called transition series, okay, for the electrons. So this series are dependent, okay, are dependent on the final energy level that they have. Okay, so for if your final energy level is 1, then you have what we call as the Lehman series. Okay, Lehman series. So you can come from whatever energy level. You can come from energy level number 2, you end at 1. Okay, energy level number 6, you end at 1. Energy level number 9, you end at 1. As long as the final energy level in that transition is 1, then we are going to call that as the Lehman series. Okay, if the final energy level is 2, like the way we had there here, okay, that one is the Bauma series. Okay, not Palmer. For those Chelsea fans, you get excited that Palmer is in chemistry. No. Okay. It's Balmer series. So if the N final is 2, then we're going to have the Balmer series. Okay. And then if the N final is 3, we have what we call as the Paschen series. Okay. We have the Paschen series. If my N final is 4, okay. And then I have what we call as the brackets series. Okay. And then if my N final is 5, I have what we call as the P fund series. Okay. So that those are enough for you. Okay. Those are enough for you for your level. So depending on which series you are in, okay, you always know the type of radiation that you are dealing with. So if you are in the Lehman series, then the radiation is ultraviolet. Okay. If you are in the Balmer series, the radiation is visible light. Okay. And then these three, going all the way to wherever you can go. Okay. Any final is 100, wherever you can go, as long as from 3 going upwards like that. Okay. The radiation will always be infrared. Okay. Infrared radiation. So it means you just have to memorize for 2. So if you are dealing with the Lehman series, you know it's ultraviolet. If you're dealing with Balmer series, okay, meaning N minus 2, they're dealing with visible light. And then any other series, okay, or any other energy level. Okay, we say the energy level is 100, that is greater than 3. So it will be infrared radiation. So based on this information, we can simply answer this. So saying what type of radiation? Okay, because the N minus 2 here, we know that we have the Balmer series, and the Balmer series have what? The visible light. So that's the radiation that you put there. Simple and straightforward. And then which series? The N is 2. So the series is what? Balmer series. Okay, so make sure you memorize this information. It's going to be very helpful as you are solving questions on atomic structure. So let's solve another question. Okay, so here they're saying, what here now? They're saying on the emission spectral lines, okay, for B and then 3 plus. So this is just beryllium. Okay, this beryllium has a wavelength of 253.4 nanometers. Okay, for an electronic transition, okay, that begins in the state N5. So meaning my initial is 5. What is the principal quantum number of the lower energy state corresponding to this emission? Okay, so in short here, they just want us to find the N5. Okay, okay, and then they're even giving us a hint here. They're saying the Bohr's model can be applied to 1 electrons ions. Don't forget the Z factor, which is the nuclear charge. Okay, so here, what are we going to use in order for us to find this NF or the N final? Okay, or the final principal quantum number or the lower principal quantum number. Okay, so we're going to use what we call as the Rydberg's equation. Okay, so the Rydberg's equation is given by 1 over the wavelength is equals to Z squared and then RH. Okay, and then in the brackets, I'm going to have 1 over N final squared minus 1 over N initial squared. Okay, so in most cases, when they are given these formulas, this thing here won't be here. It will just be like this. Okay, why? Because they assume we're dealing with hydrogen. So it means the Z will just be 1, meaning Z squared will still be 1. Okay, but here we're not dealing with hydrogen, so we have to indicate it. Okay, so here we're dealing with beryllium. So when you go on the periodic table, beryllium has 4 protons. So that's the atomic number. So Z will be 4, meaning that Z squared will be what? 16. Okay, and then this RH is what we call as the Rydberg's constant. It's given by 1.097 times 10 to the power 7 like this. So that's the Rydberg's constant. And then this is the Rydberg's equation. Okay, so whenever you're just given maybe the wavelength and then they're asking you about the energy levels or the quantum numbers or the n's, just know you have to use the Rydberg's equation. It's the only equation that connects the wavelength, okay, and the shells directly. Okay, or they give you the shells and then they're asking you about the wavelength. Just know Rydberg's equation is going to help. So here we want to find this guy. So let's try to make him the subject of a formula. So I'm going to divide both sides by Z squared RH. Even here, I'll divide by the same. Okay, so I divide this by Z squared RH. Okay, so dividing by z squared RH is the same as multiplying by 1 over z RH. So this is 10, right? If I divide by 2, okay, no. I said this is 10. Then if I multiply this 10 by half, it will give me 5. So dividing 10 by half is the same as multiplying, dividing 10 by 2. Okay, let me say that. Dividing 10 by 2 is the same as multiplying 10 by half. So this is what I mean here. So I'm dividing all this thing by z squared RH, right? So dividing this thing by this is the same as multiplying by 1 over this. Okay, so that's what I'm going to have there so that you're not confused. So I'll just say on my left, I have 1 over lambda multiplied by 1 over z squared RH is equals to, here I have 1 over nf squared minus 1 over ni squared. So I'm going to make this the subject, so this guy goes to the other side, okay? So it will just be n final squared is equals to, here I have 1 over lambda z squared RH. This guy goes there, so it will be plus 1 over ni squared. Okay, so that will be the formula that we're going to use to find our n nf. Okay, so this one should be 1 over, not just nf, because I've just gotten this and took it to the other side. Okay, so that's how it should be. So let's try to find or plug in some values. So this is 1 over nf squared is equals to 1 over. Okay, so now notice here, the wavelength here has been given in nanometers. So before we use it in our calculations, okay, we need to convert it into meters. So we know that this nano is just 10 to the power minus 9 from the metric system. So it means the wavelength is the same as 253.4 times 10 to the power minus 9 and then meters. Okay, this nano has been replaced by this. So that's what I'm going to write down here. So it will be 253.4 times 10 to the power minus 9 as my wavelength in meters. And then my z squared, okay, we found it was 16, and then multiplied by my Leibniz constant, which is 1.097 times 10 to the power 7. Okay, and then plus 1 over. So the n final, the n initial was just 5. So this will be 5 squared like this. So that's what we have from this formula here. You can all see it. Okay, so now what remains is just the issue of punching onto the calculator, but be careful how you punch. Okay, so let's do that. So I'm going to punch this whole thing on my calculator. Okay, so confirm with your own calculators as well. So how am I going to do that? I'm going to say open brackets and then I write 1 divided by open brackets. I write this whole thing here, this number here, and then I close again. Okay, so this is making sure that this thing here is in brackets like that, so that the calculator doesn't get confused. And then you say plus, okay, 1, okay, divided by 5 squared is just 25. So this is what I'm punching on my calculator. Also punch it, okay, I'm getting 0.062483,648. Okay, and this whole thing is over 1. Okay, so now to find our NF, we're just going to swap this. So this one goes on top, the one comes down. You do the same on the right-hand side. The one goes on top, this guy comes down. Okay, that's a shortcut that we can use. So we're going to say N final squared is equals to 1 over this whole thing. Okay, so punch this onto your calculator. It's giving me 16.00418. I wrote 2 4s there. So 418718. So confirm with your calculators, please do. Okay, so it means NF will just be the square root of this thing here. Okay, not NF the musician, no, but just NF like the final energy shell. Okay, so when I take the square root of this, it will be 4.00052 and then 3364. So I can just approximate round this off, it will just be 4. Okay, so it means the final energy level is 4. So it means this electron in this beryllium atom made the transition from energy level number 5 to energy level number what? 4. Okay, so that's the answer there. Okay, that's the principal quantum number of the lower energy what? State. Okay, let's do number 3. Okay, so number 3, they're saying an atom of a particular element, okay, is traveling at 1% the speed of light. Okay, the wavelength is found to be 3.31 times 10 to the power minus 3 picometers. What element is this? Okay, and then they're saying prove it, also write its electronic configuration. So this is a very nice question. So we have to understand it, okay, and then calculate. So here we've been given the speed, okay, and the wavelength. Okay, we've been given the speed and the wavelength. So since here we want to identify the element, right? We're going to use that wavelength that we've been given and the speed to find the mass. Okay, and when we know that from the mass we can actually find um, the atomic mass. Okay, since we have the mass, we can easily find the atomic mass by a special relation that I'm going to show you. So here, the speed of light, okay, the speed of light is 3.0 times 10 to the power 8 meters per second. Okay, so this particle is traveling at 1% of this. So it means the speed of this particle is 1 over 100, which is the 1%, multiplied by 3.0 times 10 to the power 8 meters per second. Okay, so punch this onto your calculator, you get 3.0 times 10 to the power 6 meters per second. So it means it's traveling at this speed, which is just 1% of the speed of light. Okay, and then the wavelength, notice we've been given in picometers, 3.31 times 10 to the power minus 3 picometers. Okay, so we have to change it into meters. Okay, so recall, recall that pico from the metric system is 10 to the power minus 12. Okay, so the first topic that you learned in chemistry. So I'm going to replace this pico with this. So it will be 3.31 times 10 to the power minus 3 times 10 to the power minus 12 for the pico and then meters. So this will just be 3.31 times 10 to the power minus 3. Oh, no, not to the power minus 3. I can combine minus 3 and minus 12. That will be minus 15 meters. So this is my wavelength in meters. Okay, that is my wavelength in meters. So I have my wavelength in meters. I have my speed in meters per second. Okay, I can calculate the mass. So we're going to use this formula to calculate the mass. We're going to say mass is equals to Planck's constant over lambda, okay, which is the wavelength, multiplied by the speed. Okay, but where does this formula come from? Okay, just comes from the formulas that we have. So we know that the wave equation is given that the speed is equals to the frequency multiplied by the wavelength, right? So I can make the wavelength here. I can make the frequency to be the subject of the formula, to just be frequency is equals to the speed over lambda. Okay, and then I also know that I have two equations for calculating the energy. One is the Einstein's formula, which says that energy is equals to mv squared. Okay, the other formula for calculating the energy, okay, it's just for the atomic structure part, is that energy is equals to Planck's constant multiplied by F. So where there's F, I'm going to put V over lambda. Okay, so energy is equals to this. Again, energy is equals to this. So I can equate this part and this part, right? Okay, so if I equate that part, I'm going to have m v squared is equals to hv over lambda. Okay, so I just want to make m the subject of the formula now. So I'll divide both sides by mv. So I'll just get m is equals to hv over lambda. Okay, so dividing by v squared, because I'm dividing this whole thing by v squared, it's the same as multiplying by 1 over v squared. So from there, we see that this v cancels, one of these v's goes. So it means m is equals to h over lambda v, which is this formula. Okay, so we know where the formula is coming from. Let's plug in the values. We find the mass. Okay, let's plug in the values to find the mass. So I've kept those values. Okay, so we're going to say mass is equals to Planck's constant. We know its values, just 6 point, okay? 6 point, okay, I want to show how the units are coming about here. So we said the speed is this, right? It has meters per second. Then the lambda we found it was 3.31 times 10 to the power minus 15 meters, right? Okay. So the Planck's constant as the units J multiplied by second, right? Okay. So now this J here is the joules. So joules, if you express it in its basic unit, it's the same as kg multiplied by meter squared, okay, divided by s squared. This is my joules. This is what joules mean. Okay. So I'm going to put the units here. Okay. Or I'll show them later anyway. So let me put first of all the numbers. So this will be 6.626 times 10 to the power minus 34. This is the Planck's constant, right? Divided by lambda 3.31 times 10 to the power minus 15 multiplied by the speed, which is 3.0 times 10 to the power 6, like this. Okay, so now you can put this in brackets on your calculator, this in brackets, and then see what it's going to give you. So there it's giving me 6.672708963 times 10 to the power minus 26. Okay, so this is the answer that I get, and this is the mass. But what are the units here? Okay, what are the units here? So I need to show this. So remember the Planck's constants, the units are joules multiplied by second, but we said joules expressed in its basic units is this. So on top there, I'm going to have kg meter squared over s squared multiplied by, this whole thing is just j, multiplied by this s, and then divided by the lambda here. Okay, the lambda here is meters, so it will be meters multiplied by the speed is meters per second. Okay, so from here, what do we see? Okay, we see that on top there, this one cancels with one of these, so I just remain with kg m squared over s divided by, here I have m squared over s. So I can change this division side to a multiplication side, and then I swap these, right? Okay, so that's exactly what I'm going to do. I'm going to say this is now multiplied by s over m squared. So we see m squared goes, s and s goes. So the units here are kgs. Okay, so the mass that we find using this formula is in kgs. Okay, so now that we have the mass, which is in kgs, it's going to help us find the atomic mass. So remember, in topic 1, we said one atomic mass unit is the same as, okay, 1.661 times 10 to the power minus 27 kgs. That's what we said in topic 1. So we're going to use this relationship to find atomic mass unit. So this will be 6.67270893 multiplied by 10 to the power minus 26 kg, and then x. So cross multiply. Okay, so this will just be x is equals to 6.67270893 times 10 to the power minus 26 divided by 1.661 times 10 to the power minus 27. Okay, so that is going to give us the atomic mass units. So just put this, okay, on your calculator. Make sure you put them in brackets, even this in brackets, okay, and then divide them. So the answer that I'm getting there is 0.172844144, like this. So these units here are now going to be what? Atomic mass units. Okay, so we can round this off. It will be approximately 40.17 atomic mass units. So to identify which element it is, okay, which element it is, we just look at the atomic mass unit. Okay, this is the atomic mass. So we go on the periodic table and check which element has the atomic mass which is closer to this. Okay, so let's go and check. Where's my periodic table? It's here. So from this, my periodic table here. Okay, what's happening? Okay, which element has a number that is very close to 40? Okay, so remember there I found 40.17. Okay, so the atomic mass is these numbers that are below here. So they go in order from 1 point something, they're increasing like that. So 40 point something, this is 39. Okay, so it can be this one. This is 39 as well, and then this is 40. Okay, so for calcium, it's 40.0 something. So we see that this here is closer to this. Okay, so it means the element that we are dealing with there is actually what? Calcium, based on the atomic mass unit. So we're going to say the element is calcium. Okay, and then what is remaining is just to write its electronic configuration. So the electronic configuration now, okay, we just look at the periodic table. We see that calcium has 20 protons. So 20 protons in calcium simply means 20 electrons. Okay, so the electronic configuration now here, we have to write it in terms of the sub levels for the orbitals, okay, not the secondary level. Okay, so I'm going to say N here, and then here I'm going to say sub levels. Okay, so remember the sub levels when we are solving tutorial sheet. Is that this is tutorial sheet what? Oh, this is the assignment. When we're solving tutorial sheet 7 and 6, that is atomic structure. We said if we have S, okay, if we have S, then, okay, this S can hold up to 2 electrons. If we have P, this P can hold up to 6 electrons. D can hold up to 10. F can hold up to 14. Okay, and then if my N is 1, then it means I only have one sublabel, which will be the 1s. If it's 2, it will be 2s, 2p. Okay, if it's 3, I have 3s, 3p, and then 3d. If it's 4, okay, if it's 4, I have 4s, 4p, 4d, and then 4f, like this. Okay, so how do we write the electronic configuration? We follow these arrows. Okay. So we fill in these sub levels, okay, or the orbitals in this direction. So it will be, first of all, it will be the 1s, and then the 2s, and then 2p going to the 3s, and then 3p going to the 4s, like that. Then 3d going to the 4p, just like that. We're going to be following these two arrows. Okay, so I'm going to say the electronic configuration of calcium is equals to 1s. This 1s here, only can contain 2. And then I go to 2s, can also contain 2. Then I go to 2p, because I'm following this arrow where it's starting from like this. So I go to 2p. So 2p, we know that p can hold up to 6. Okay, and then I go to 3s, which can hold up to what? 2, because it's s. Okay, and then from there I'll go to 3p. 3p can hold up to 6 as well. So let's count first of all, because we have 20 to distribute. So this is 4, 6, 10, and then this is 8. So I'm remaining with 2. So those 2 will be in the 4s here, because I'm going like this. So 4s will also have 2. So this here is the electronic configuration, okay? Is the electronic configuration um, for calcium. All right, so thank you so much for watching. If you'd like to access the full solutions to this assignment, okay, plus all the other tutorial sheets, okay, plus past papers, plus topic lessons, okay, feel free to register with us. You can just check the link in the description below, okay? It's going to give you a link to a registration video guide, so you can watch it and know how to register on our website. All right, so if you'd like to access full solutions to the assignment or even the tutorial sheets or past papers, okay, I'd like to tell you that we do have those on our website. So this is assignment 2. Okay, we solved all these questions and the solutions are there on the website from question 1 all the way to question 8. Okay. In case you are behind, okay, and you want to learn concept from the very first class that we had, okay, we have videos on tutorial sheet 1. So this was tutorial sheet 1, units and conversions, to get the basics that you're going to be using in the entire course. So we solved all these questions for tutorial sheet 1. Okay, the videos are there on the website. Tutorial sheet 2, this one here, which is on atoms, isotopes, we solved all these questions. The videos are there on the website. Tutorial sheet 3, we can see here empirical formula, dilution formula, all these questions we solved, the videos are there. Got tutorial sheet 4, which is on balancing electron equations, I mean. We have some questions on Henry's law. Okay, we solved all these here. Okay, percentage yield, we solved this question. This was tutorial sheet 4. Tutorial sheet 5 was on titration. Okay, or solutions to stoichiometry, we solved again. All these questions are there. and on oxidation numbers. We solved 4 video solutions are there, so you can use them to learn at your own time. Okay, and then we went to the tutorial sheet for atomic structure. So you can see this was the first tutorial sheet on atomic structure. We solved all the questions that they are solved. And then this was the other one, atomic structure. We solved it again. All the questions here have been solved from question 1 all the way to question 13. Tutorial sheet 9, which was on chemical equilibrium. Again, we've solved all the questions here. So you can access them, you can learn at your own time, at your own pace. Okay, I explained all the concepts that are here. Even the video for tutorial sheet 1, as well as the written solutions full, are there on the website. All these questions here. Okay, the solutions are there on the website. So feel free to register on our website. You'll be able to access all these. Okay, so let me show you um, our website. Okay, so you can see here, this one is just finishing up uploading. That is that tutorial sheet 7. Um, let me show you how the website operates. Okay, so once you are enrolled and you come on our website, you see something like this. Okay, you can see the course is saying enrolled there, meaning that you've enrolled for that course. Okay, so to know how to enroll, there's a video in the description below here. You can watch it and know how to subscribe. So if you subscribe for chemistry, you can open it and then you go in this folder for general chemistry. Okay, if you are first semester Apex or you are at any other university. Okay, and then if you are second semester Apex, you come to this folder. But that's first semester, so I go to first semester general chemistry. Okay, so this opens. Here we have lessons and tutorials. So each topic will be explained in full, and the videos are there waiting for you. Okay, so there are videos and notes, and then here there are handwritten notes summarizing the key things that you must know. So you can also study these handwritten notes. And then here we have the tutorial sheets and assignments, past papers, and some lab report samples. So as you prepare for your tests, your exams, your quizzes, make sure you know how to solve the tutorial sheets. So when you open this folder, you go to the folder for your university. So if you're from Apex, for example, you just click Apex. Okay, click Apex, and then there are different intakes here. So the current intake right now is 2025 July intake. But even here, there are full tutorial sheets here, and the concepts are the same. So you can still watch those videos if you want. Let's check the 2025 July intake. Okay, so you can see here, these are the videos. So this is the video for assignment 2. Okay, um, assignment 1, full written solutions. Assignment 2, full written solutions are there. You can see them. And then tutorial sheet 1 is where? Oh, this is the video for assignment 1. And then as tutorial sheet 1 video is there. 2. So the tutorial sheet 2 are divided into 3 parts. There's this part, this one, and this one. But tutorial sheet 3 is just one video is here. Tutorial sheet 4, tutorial sheet 5. Tutorial sheet 7, we had 2. Okay. 2 tutorial sheet 7s. So they are on both atomic structure. So you can see this is the first one. The other one is there. Okay, and then chemical equilibrium is here. So everything that you need is there in order to help you pass your upcoming assessments like quiz 2, test 2, the exam. They're here. So you learn at your own time, at your own pace. Okay, so you can watch this. And then if you also want to access some past papers, okay, you go to the folder for past papers, which is past quiz, test, and exam papers. So if you open that folder, you're going to find the similar arrangements to the tutorial sheet assignment folder. So open Apex, okay, or any other university where you're from. You go to the video solutions here, okay. So if you go to the video solutions here, it's just loading. Give it some time. Okay, so these are the videos. So you can see we have videos for the final exams, like those. Okay, we have videos for test ones. You can see the test ones there. And we also have videos for quiz 2. So as you're preparing for quiz 2, okay, you can watch this video for the last intake quiz 2. Okay, just to get the idea. We have quiz ones here. There's also another quiz two here, test two, quiz two again there. So you can use these to prepare for your assessments. Okay. So feel free to register with us. Just check the link in the description below to know how to register for our lessons. Okay. And if you don't understand something, okay, we have video lessons for all the topics. Okay, so you can go in this folder, lessons and tutorials. You are going to find different topics. Okay, so depending on the topic that you want, you can see the more concepts, empirical, redox, whatever topic that you can talk about in chemistry. So the lessons are already there. You can learn at your own time, at your own pace. So thank you so much for watching. This has been Tutor Poul Solutions. Until next time.